So yeah, I could talk a little bit more just the calculus part, and I could talk along physics. So up to you guys, but of course it's best to eventually have to do both, right? Bill, are you okay? Anybody else? Where's Frank?
Frank said he has a creative writing piece that he's working on.
Frank. Okay, let's wait for Frank, then we can start. I think Nick said he has something else. He probably won't be able to join, and also he felt it's probably too challenging for him for now. Oh, where's Leon? Bill, are you able to speak? Where's Bill? Okay, let's start. We can only wait for maximum 5 minutes. So here, let me switch to my screen. Okay, here. Let me see. Okay, cool. So let's see what we're going to talk about today. Maybe I will start with
speech to text or whatever it is. Oh, salutaris hostia.
So I'm going to start with actually talk a little about this delta. I think it's will be Chris is on, I think. So I like to today. I like to start with today I'm going to talk a little bit first and continue to talk a little bit about the math session, and then we go back to physics, continue our physics discussion, and so today let's talk about this delta dx, right? Typically, no matter in our derivative, we typically say d a function dx. So that means this function regarding to x derivative, or in our integral we say this is function we integral for x. Okay, so like to talk about this piece a little bit today. I think that is one of the very important you know, element of this whole you know, derivative and whole calculus. The reason, so remember, what is this dx? This dx is basically is delta x, right? The change of x, and however we have to approaching to infinite small, right? Approaching so-called zero. However, it is not exactly zero. So I sent you one of the video clip from YouTube talk about, you know, try to understand calculus from a 5th grade math. I think it's taught by a Stanford or MIT college student, said the exact same thing. So this you know, this become dx, right? So but dx is not zero, okay, but it's approaching to zero. So this is an important concept which doesn't exist before calculus, right? Before calculus didn't have this concept. So now, so why this one is important? For example, so you can deal with this one like the way you want. For example, when we do the derivative here, it means dfx dx. You can treat this guy like you know, like doing all kinds of operations. For example, this one leading to dfx equals to, you can do this, right? Just like you treat it just like you know, regular, you know, operation thing. So you can time both sides dx, right? Become this. You can definitely do that, right? It's fundamentally is one of this. So therefore, you can do all kinds of those operations. For example, from here you can say, oh, let me do the integral on both sides. So therefore, you know, this integral of you know, a d change eventually becomes, you know, fx. So this side is basically, right? So you can do this kind of operation, no issue, okay? So another way you could do is, for example, you could do, for example, if I say x equals sine theta, let's say x equals sine theta, and you can still do the dx equals to what? Dx equal to sine theta, derivative become cosine theta d theta. So why is this? So why is this? Right? This is kind of like you. This is very widely used in the calculus to deal with this kind of treatment. So why this one is true, and you know, so why this is true? So if you really read this one as a function, right? X is a function of theta, right? So I can do dx dx, which means I can do this kind of, you know, derivative. So dx, you know, this kind of derivative, actually you can do this, right? So this one equals to what? This one equals to cosine theta, right? Sorry, it's not really. So this one is basically, this is theta, this is dx. You cannot do this way, but you could do is change to d theta, okay? Then you can have d theta dx. So this one, actually, you can say this like operation, you can cancel them out, right? They still go back to here, right? So in that case, this one you will know, sine theta d theta we know is cosine theta, right? Very easy. So this one is d theta dx, right? So and from here, and then you go back means dx, you still both side time dx. This one means cosine theta d theta, so which is here. Okay, so this is basically this is basically the kind of treatment you can do and widely used in the whole calculus, especially in the integral. Sometimes we do this kind of replacement. I'll give you more example later. So you know, it's quite often we do this kind of treatment. For example, if you say, okay, u equals to x minus a, and so I want to do du, which is dx minus a, eventually it's dx, because the dA is basically, because a is constant, is 0. So this is basically come to du dx. So why is this? Right? If you hard to understand, you just treat it as a function, you do a du dx, right? Dx minus a derivative. So this one we, this one we know is dx dx, right? Because dA's derivative is 0. So this is basically du dx. Okay. So this is all kind of thing you can do. Yeah, I think that's from here, of course, you can also do d theta equals to dx divided by cosine theta, correct? This kind of treatment is widely used in the calculus. It's kind of small scale, and I want to talk about today little bit. Okay, so so this is dealing with this kind of d small d thing. Okay, so this part has any question? So we frequently use when we do some kind of treatment in the calculus, in the integral, for example, a lot of this kind of treatment, and it's all based on what I said here. Okay. So this is fine. Let's say how to use this one. Give you example. For example, let's try to say we have a rope, we have a curve, or we have an arc. Okay, so this one, let's see, this is f function regarding to x, right? This, say that this x, this is y. So this is function x. So we want to know how long is this curve. So from, say, for example, let's say from x1 to x2, how long is this arc or this curve? How to do that? How to calculate once, if I know this function, let's say this function is random. I write random, write anything. This is power, right? So how can I, this is x squared or x cubed, whatever function is, how this, of course, is a curve, and how do I know the exactly length? This one, how to get this? We call the arc length problem. So Frank, have you guys learned this during your calculus class?
Yes. So we learned the normal Cartesian plane arc length. We learned polar arc length, and then we also learned the parametric arc length, which is like you implicitly differentiate the x and the y. Okay.
So this is basically using the one I mentioned. So if you really look at one of the tiny segment here of this arc, so you are saying, oh, how long is this one? So this is, we call it ds length, right? Okay. So what is ds? Let me zoom out. This is ds, right? So then has so you create a right triangle. So this is dx, this is dy, correct? Right? Basically dx horizontally, the small difference here, and is a vertical follow this this curve. So this is a segment of this length. So eventually we want to say ds equals to what? So based on the Pythagorean theory, dx squared equal to dx squared plus dy squared, correct? Okay. So then ds equals to square root of, dx squared plus dy squared, right? Right, it's all dealing with this, all dealing with, I just talked about this dx or dy, dz, those kind of things, or d theta, whatever. Okay, so now from here, so I want to, because I want to get the whole arc. Okay, so what I do is I integral ds, right? I integral ds and become integral this whole thing. Sorry. Just integral this whole thing, right? Same, okay? So here, basically what we can do the treatment is, if I take this one equals to 1 plus dy dx squared dx, right? I take the dx out, right? Then of course divided by dx squared bottom and become this one, right? There's no issue, right? So say this one becomes basic integral 1 plus y derivative, let me write this way, square dx integral from x1 to x2, right? So this one basically gave you this whole length, correct? This length, this s equals to.
Dr. Wang, could you just clarify to them why you want to go from the dx squared plus dy squared to the 1 plus dy dx squared? Like, why would you do that operation?
Oh, you mean do here, this operation?
Yeah. Why would you bother taking that step if all you're doing is an algebraic conversion? I guess what I'm trying to get at is that, like, you want it, that dy is essentially a function of x, and then you dy dx is basically the derivative of that. So what you essentially want to do is to just take the derivative of the arc length of the original function.
Right, exactly, yeah. So this one basically convert into the way we understand well from our integral concept and with the differential, derivative here, right? So this one become a general formula. You can calculate y, function regarding x, what kind of length, right? So for example, let's take example. Let's take this example. So if I say y of fx, this line is x, 3 power 3 over 2. So can I get the general formula of how the length calculate? So then therefore this length equals to the arc length equal to integral, right? So 1 plus this one's derivative is what? This one derivative become 2 third x. 2 third minus 1 is 1/2, right? dx, right? Got it? Oh, sorry, this one has to be square, correct? Correct? This is, so because this is y, so then y, the derivative becomes minus 1, right? X 1/2, okay? So this put in, got here, then you can continue. So this one becomes 9 4x dx, correct? So it's how to do this kind of integral. So I'm looking for anti-derivative of this function, so which will be the integral, this whole thing, right? This was integral concept. Any question? So typically we do this, we have used a trick. The trick is what I just talked about. You treat u equals to 1 plus 9 over 4x, right? Then du equals to 4 9 dx. Okay, this is what I just talked about. Okay, if you want to prove, you go back to that to prove. So this one you become dx equals to 4 9 du, right? Then you put this one back, and this one becomes square root of u, correct? This is u. Dx equals to 4 divided over 9 du, right? So then this one becomes 9 u 1/2 du, correct? Right? So this one is easy. What is anti-Dirac of this one? So basically is anti-Dirac, this one has to be u, this one, right? This one derivative becomes this function. Then you have to take it out, then have to do this. So this, because this derivative is u power 1/2, right? So basically that's it. And then you need to add a constant because we are looking for the whole derivative. So you have to eventually, we said, have to from x1 to x2. So then we go, yeah. So u is u, we put it back. U is 1 plus 9/4 x1 to x2. So this becomes the final length. And so basically it becomes, if you really write out, is 27 1 plus 9/4 x2 then minus 7 x1. So this is the final length of the arc of the curve. So this gives you a quick example. So you can solve by basically any functions if the curve length of any function, right? Some are easy. So this one actually is quite easy. I intentionally pick an easy one to two actually. Okay. So for example, if you can try if this is x equals x squared. So this actually looks much simpler function originally compared to x power 3/2. However, this one is much harder to do this integral. You can give a try. It's a lot more harder, right? And I think I have here. Yeah. So this one is much harder, and I don't want to go over here. So basically, here is if x power 2 and so divide the x equals 2x, and the same thing, you integral this here, for example, then become like here. So become a square root 1 plus something square, x squared, and try to do integral. It's not easy. This one is much harder integral problem compared to the other one. So this one becomes we do the same thing. We use u equals 2x, and it become 1 plus u squared, square root of that du the derivative. So then we have to use the trigonometry function to help us. So basically when u equals tangent theta, du equals this one, and then put it back here, and it becomes, you have the integral of second theta cubic d theta, but eventually you can get there, but it's much complicated. Okay, you see, have log natural lag function here, and it's harder to do integral. Okay, even though look like this one is simpler beginning, but it's harder. It really depends, right? This is a little bit different nature in terms of integral, derivative, antiderivative, which function. Some function look like complicated. Actually, when you do it, really found that it's easier. But someone, because of the relationship between integral and derivative, anti-derivative is quite interesting relationship. Got it? So I don't even want to go over here too much here, but you get the concept, okay? So this is how we use this kind of delta S, equals this when each of them approaching really infinity small, then become this, and then this become here, then this how you get this whole, very simple, right? Very simple how to derive the arc length, okay? Curve length. Okay, got it? So this is a little bit of math I like to share with you today, and go over a little bit here. I do have one. I do have, you know, this example we already went over. Basically, this is this you know, 3/2 example. Eventually, you get here, right? And so I have another example here. Is basically is if x cubed divided by 6 plus 1/2x. This is a curve. We want to, this curve look like this kind of shape. We want to integrate the, you know, a portion to get the arc length. So this one's derivative become here. It's easy. Then you integral according to the formula, integral, you know, this whole thing square in the dx, and then you open up, and then you do this, and you just continue to do the treatment. Eventually you get this guy's integral, so which you can do. So this one is actually is not that hard to do, and you can still dealing with the power function. You know, it's like that. Okay. Got it. So this is just a quick example to that, and now I have two. I will let you guys decide. You want me to give you how to use integral or mass to solve a mass problem? For example, why the sphere's surface area is 4 pi r squared, or why the volume sphere is you know, 4/3 pi r cubic? This kind of problem use integral. You want to do this one today, or you want me to go back to Newton law to talk about the Newton law and you know, physics part? Any preference?
I prefer if we went back to Newton.
Okay. Any other idea? Want to go to Newton law?
Yeah, I would agree with Alexandra.
Okay. So let's do Newton law. Okay, wonderful. Let's do physics part. Okay. Let's do physics part. We can come back to this one later. That's fine. So physics part, actually, I want to talk about this. I want to give you some using the math tool. The math tool is really powerful. The calculus math, this tool is really both integral and derivative. We call differentiation. It's really powerful. Let me show you, okay, what we can do here. I think many of them you may not learn from your physics class in school, and typically school doesn't teach this way. But I thought it's you know, because when I try to digest every physics piece I learn, I always like to put everything under one roof, and so I can make the physics very simple. I don't like remember formula, so that's why I always prefer a very logical system. So therefore, I can understand. Sounds like pretty complete concept. Let me give some example. For example, I remember Leo mentioned a formula in the projectile movement, saying that v squared minus v north squared equals 2as, something like this. This is one of the formula in the free fall movement. One of the formula which you can connect velocity and the distance directly without involve the t. Okay, of course you can derive that one from once you have once you have v equals v0t plus plus g, sorry, v equal v0 plus gt, and you can see I'm not very good at formula, but I have to go back to my principle. So, and also distance equals to s0 plus v0t plus 1/2 gt squared. So you can use this one, cancel out the t, and get this formula. Okay, got it? Yeah. out here is a G. Oh, here is A, doesn't matter. So this is formula, right? But what is formula? It's let me prove you this way. So this actually is energy conservation. You may not realize it's energy conservation, but it is energy conservation. Why? Because if you time both sides by 1/2 m, so basically 1/2 m v squared minus 1/2 m v naught squared equals to mgs. So this is energy conservation, saying that the kinetic energy equal to initial kinetic energy plus the gravitational force or weight, the time distance, which is we call it potential energy, or we call it the power, the work the force does. So this is basically the energy conservation. Okay, but where did it come from? So let me ask a question to any of you have learned enough physics, half-year physics, anyone. So tell me why kinetic is energy writing in this way. Why? Anybody able to answer this? So why the kinetic energy is 1/2 mv squared? Anybody know? People use this all the time, and especially when you learn the kinematics, and you use it all the time because you use energy conservation, right? Lots of time you use energy conservation. For example, when in the roller coaster you do this kind of movement, you're starting from top, and assuming there's no friction, you're falling down. This one goes this, so you can solve any position speed. And assuming you know the height, and initially you start with release or static, zero speed. You just release this one, speed up, and then do a circle, just like a roller coaster we do. So you can solve this one by using this energy conservation and potential energy plus initial kinetic energy, which is 0 because velocity is 0. And so you can any position you can see how much potential energy, and then you can calculate the velocity. But the question is, why is 1/2 mv squared not 1/3 or not mv squared, 1 times m squared? Why?
But is it because it's the integral? Because energy is essentially equal to the change in the work done by something, and the work done by something is mass times distance, which 1/2 v squared is equal to distance because it's the integral of velocity, I guess.
Yes, pretty close. Yeah. Okay, so let's go back to here. Basically, let's go back to here. So everything is here. This one, everything. Let me prove it. Let me prove to you what we can do with this formula, with math knowledge we already learned. So everything else is all here. Energy conservation, momentum conservation, momentum impulse law, and everything. So it's quite interesting. You just look at the formula, you have the calculus base, you got everything basically. Why? F equals to ma. Ma is dv dt, correct? Okay. And so just like Leo said, according to if we both side time s means force time distance, which means the work equals to m dv dt time s, right? Oh, actually, we should say F times delta S, because times the change of the, the distance. So this is delta S, delta X, right? Okay, so this actually becomes m delta S dt dv. Delta S, of course, when the force and the movement, the position movement is is keep changing. So eventually you need to do is change this one become infinite small delta S, delta S, delta S. Then you do integral, correct? Right. So that's a total work it is. So this one becomes m is constant. You can take out this one. ds dt actually is v dv. So this is y is 1/2 v squared. Of course, v1 to v2. So that is basically 1/2 mv2 squared, 1/2 mv1 squared equals this one equals the total work. Cool. So this is basically why this is called kinetic energy. This is EK. Kinetic difference equals to the force work. Okay. This is nothing. Just a little bit mathematical treatment, right? Right. Okay. So and let me go over. Okay, so basically, so this is nothing else. This is basically the energy conservation. Okay, this part is kinetic energy. That's what you learn in school. And of course, most case school, I forgot how did you guys teach in high school about this formula, but this is what the right place to understand why is 1/2 mv squared. Okay, and okay, so now the next one explain is this, right? So F equals m dv dt, right? So and if you move m in, become dmv dt. So because m is constant, so this become dp dt. So that's why we call the P equals mv. P is called the momentum. Got it? Okay. And so if you time delta t both sides, F times delta t equals dp. So this is basically the impulse. This is called impulse, force time impulse. So this is momentum change. So basically, under what kind of condition the momentum is conservation? Means if dp equals to 0, means the momentum is conserved. So p2 equals p1. So that is happen to be there is no external force. If the external for a system external force equal to 0, then delta p equals 0 means momentum conservation. So that happened to be like, for example, you have on a frictionless surface, you have 2 blocks, and this one travel is velocity v m1 m2. They knock onto m2 or m2 also this way. They knock each other, and then they are keep. Then you can use momentum conservation law. It's coming from here. Okay, it's basic F equal ma. So everything is F equal ma. Okay, energy conservation is Fm equal ma. Momentum conservation is F equal ma. Okay, everything. The same thing, you probably learned this very famous experiment is, so you have some same mass ball hanging on here, like a pendulum, and then you move, you raise this one, and let's release, then you knock the next one, then eventually only this one become rest, and this one won't go up and coming back again. This is basically demonstrate and momentum conservation and of course energy conservation. Okay, so this is all here, coming from here. Good. Yeah, basically this one integral, and it becomes, if this is 0, this one becomes, the P2 minus P1 equals to 0, that third P equals 0. So that's my energy momentum conservation. Okay. So then then let's go back to here and talking about widely used energy conservation in many of the free fall case. We can say that energy E1 equals E2. So E equals to E kinetic energy plus E potential energy. So kinetic energy is 1/2 mv squared. Potential energy typically depends on what kind of system. Potential energy is different. For example, for a mass of mg, and as potential energy from the gravitational is always mgh. But for a spring, with a spring constant k, this potential energy becomes kx squared. So why is that? So why is here? So why this formula is correct, and why is this? So let's also derive this. So remember let's go back. So we have F equals ma equals m dv dt, right? And so we time movement along the force direction. Actually, this is all vector, but I try to make it easy for you. Otherwise, this one all vector equals to basically ds dv dt. So this becomes m ds dt dv. So this is basically, this is v definition, speed, become mv times dv. Okay, so that is then your integral every place, both places become f. This is a dot, called a dot product. So this one becomes 1/2 mv squared and v1 v2. So 1/2 mv2 squared minus v1 squared. So that is basically is coming from Newton's second law all the way to here. So that's same. So this is basically Newton's second law. Okay, just use this kind of treatment. So this is kinetic energy difference equal to the work power, the work by the force. So in here, so you can see that if like a system like we just said, like this frictionless fall roller coaster case, or like the pendulum swing, in all of those cases, or there's case like there is curve and slope, and it's frictionless. You have a block, a ball to throw along this way and eventually stop here, then coming back, right? All of those kind of thing is let's deal with it. So let's convert it. So in this case, we have force is mg. We have another force, only other force left is called N. This N is always perpendicular to your curve's tangent. Basically, this force always perpendicular to the surface, correct? Correct? Okay, so in that case, our total force for this system, is similar. You have mg, you have a tension force, which is also perpendicular to the moving direction, correct? Here is you have the mg also perpendicular to the surface. So all of those cases has a common nature, even though there are two forces, not only mg, but the other force is always perpendicular to your position movement. So in that case, you can see F dot ds equals to two forces, right? mg and plus n ds. Okay, n and ds is always perpendicular. So therefore, so basically this force doesn't generate work because it's always perpendicular to the moving direction. So that's why this only left is still mg there s. The other one is 0. So this one basically coming to mg h and h1 h2. So if you put this one back to here, and that give you actually the energy conservation 1/2 mv squared 1 plus mgh1 equals to m. So that's widely used in all your early, when you study Newton physics, widely used this energy conservation, kinetic energy plus potential energy, solving all this kind of problem. Okay, where it coming from? Okay, it's just because this. Just because this. Cool? Nothing else. Any question so far? And let's deal with another case. Let's deal with basically what I said is spring case. This is also widely tested physics problem in all kinds of your physics test. And so this is basically saying there's a spring, or the spring could be hanging over there, a block. The block has mass m. So in this case, of course, this is frictionless. The surface no friction. In this, it's just free, free hanging there, right? So k is a spring constant. So when you have some knowledge about spring. Spring is something that spring has original length, right? Rest length at rest. So if you, at that time, spring is no tension, pretty relaxed. And either you squeeze it or you pull it, and you're starting to generate, you can feel the spring will pull you, right? For example, you pull it, and longer than the length of at rest, then the spring will pull you, try to pull you back. And if you squeeze spring will push you back, push you wide. So that is spring. So spring has if you learn physics, let's say this is springs at length at rest. And then now if I move the bar, I pull this block to here. So basically spring now starting to elongate to here. And the spring, the distance change here is x. Then spring here generate a force, try to pull this block back. And if here, this is frictionless surface, if you pull here and you lose it, then this one will speed up to here, won't stop here because this then continue push into, then starting to oscillate at this location. Okay, like that, oscillate. Here, same thing here. So this one, of course, this is not really rest position because at a static position, this force already put the spring down a little bit. But anyway, so this is where it starts is like if you don't touch it, so it's spring already put down a little bit, right? Stay. But if you further pull down, and then you lose, and then it will also oscillate here. So we will come back to this kind of oscillation friction calculation later, which is another perfect example to explain the calculus and a perfect example to use calculus. But here we just understand the basics about spring. And as a spring, the basic is when you move away from as position, static position, the force pull you down. This force from spring, right? Spring force. How to write this one? This is an empirical formula. It's basically kx. The force is, you can plus whatever. The force is a constant, is proportional to the displacement by a constant, time constant. This constant called the spring constant. Each spring has one itself constant. So thicker spring may have different k than the center from the center spring, but as long as the fixed spring, this k is fixed. So this is basically this formula, okay? Typically we say we use minus because it means this the force direction is always you pull and force is pull you back. If you push down, force pull you. So force direction is different from your x direction. Okay, so that's the formula. Okay, so for this kind of thing, if you go back to here, you are fine. You are fine for this case because the mg doesn't make any work because mg is perpendicular to the movement direction, right? The only force is basically spring force. So in that case, the power, the work you do time the x, meaning the x right now, is really kx dx equals to correct? So this is why the spring for spring, the potential, now we define this called potential energy, just like we defined here called potential energy for the weight. This is potential energy for the, right? So this one, if you put back into, put back into here, so basically you get the formula is kinetic energy plus initial potential energy plus initial spring potential energy equals this. Kinetic energy plus potential energy, kinetic plus potential, so energy conservation. So here's energy conservation. Kinetic energy, potential energy, kinetic energy, potential energy, conservation. So all those system is a energy conservation case. Kinetic energy plus potential energy, kinetic plus potential energy equals 2. So basically, that's why the ball here raised pretty high, 0 speed and the release. So we're speed up because now converting when they're coming down and coming down, and so this height convert into potential energy, convert into kinetic energy. So that's why at the bottom, if you define here is a height 0, so bottom potential energy is 0. However, kinetic energy is maximum because here is the kinetic energy is 0, potential energy maximum. So you convert. So that's energy conservation. Same thing here. So when you raise the ball here before we release, the potential energy is the highest. Kinetic energy is 0 because velocity is 0. But once you release, when it comes to the lower point, the potential energy is minimum, but kinetic energy maximum. So there's energy conservation here. Same thing here. Along the whole thing, everywhere, kinetic energy, the total energy connected to potential energy, adding together, always equal to any position. Is always the same. So the same thing here. Same thing here. So this one is a little bit complicated. This one has mg. So this one you should write the formula. You can see because mg also along the movement direction. So you have 2 potential energy. So one is spring potential energy, which is 1/2 kx squared. But you also have potential energy, which is mgh, and plus kinetic energy. So this 3 term adding together is a conservation. But I try to show you pretty quick. Of course, if you haven't really learned this one, I give you a very high level and explanation, but it's a very essential explanation. So why everything is coming from just as simple as this formula, nothing else, right? Whatever I did, I have done here 2-page thing. Momentum conservation, energy conservation, everything is just from Newton's law. Everything coming from Newton's law. So Newton's second law is an essential thing. Only one formula really important. So all rest is, once you have the math 2, all the rest will be just very natural. Cool. So I explained why the kinetic energy formula is 1/2 mv squared, right? It's just because Newton law, and then I also explained energy conservation. So momentum conservation, everything is coming from here. So it's now you at least listen to this just very quick. You get the idea of physics like a pyramid, right? There are lots of different type of application, different kind of problem, looks very complicated. And the top is only one thing. One couple of equation determine everything. The rest is basically the 2 things important to physics. One is math. One is physics concept. So I in the whole process, I only have a pencil, a piece of paper. The only thing I do need is I start with Newton's law as well as 3-letter formula. And of course, I have my calculus math knowledge. And the rest is just a concept, like what is, power. But the rest is very natural thing. You know what I mean? Right? So that's what I found. I found physics so interesting to me, because I can this whole pyramid I can trace back to the only top tip, and the rest I can very self system, forming a self system. It's very easy to follow logically. Nothing really strange. You don't really need to remember much. Is that good? Okay, so that's basically you know, a little bit more physics, and now I go back to teach you. Let me move into something even more fancy a little bit. Let's see.
What's fancier than Newton?
Yeah, still, and you know, we are beyond the Newton law for a while, and only this formula F equal ma. That's it. But I want to do something even interesting thing. But everything interesting thing involve a little bit more math, because you are saying, oh, I have to deal with some variation, but it's extension. It's all relate to math. So basically, here is something I like to talk about. Remember last time I talked about, you know, in XY system, this is a position vector, and at the project on both direction is X position, Y position, X coordinate, Y coordinate. So which really means this R vector, it can be written in X along X direction component plus Y along Y direction component. Okay, then from here you have vector, then the velocity definition is vector's change rate according to time. So dr dt, so that eventually becomes dx dt x direction, dy dt y direction. So that become x velocity x direction plus y velocity y direction. So then the total velocity amplitude equal to those two Paragonson theory square plus this square root. And then the acceleration is a velocity vectors rate, changing rate. So it's basically doing twice of derivative of vector, I mean the position vector. So eventually becomes dx dt double twice derivative, x direction, 12 derivative, y direction. So the velocity amplitude equal to this. So basically, F equal ma, F also x direction, y direction component. So then x direction equals m equal m x, you know, y equal this. So basically decompose everything into an XY system. It's pretty straightforward, right? Then of course the example is this kind of projectile and the movement to different direction, follow to different you know, very simple. You can derive all the formula you want. It's very simple. There's nothing. Look at the whole page is you know, very you know, very messy, but actually you don't even need to remember those. As long as you remember F equal ma, decompose two direction, and then calculus, basic calculus knowledge. For example, if you know a equals dv dt, and what is a, and then you can know what is v, which is anti-derivative. Then you can easily derive those formula and whatever this formula is, right? Okay, so this is one Newton physics, Newton law under this geometry. So now I'm going to switch to another system, describe a pretty much a similar thing. Is basically now I will say I have a movement on the surface, two-dimensional. So this is my position vector. but I'm going to decompose it using theta, r theta configuration. We call it polar geometry. So in that case, you can see that projection along this direction becomes r cosine theta, and along this direction becomes r sine theta, correct? Okay, so in that case, r is really r cosine theta. I will use I for x direction vector, j for y direction vector, r sine theta j direction. Is that true? Simple? Okay, then I'm going to do same thing. What is velocity? Then it's dr dt, right? So this is a very general case. Let's don't do specialization at this moment. Really means that this r can change with time, theta can change with time. Okay, so r itself, this length itself, including direction, both can be time dependent. So basically, r is a time function, theta is time function. So in that case, so when you do the derivative, so you have to use derivative law, which really means, of course, this unit vector doesn't change, x, y. So therefore, di dt equals to 0, dj dt equals to, they are not changing with time, but the rest changing with time. Then how to do that? So basically, you involve d dt r cosine theta, right, plus d dt r sine theta j, right? So this whole thing has to be derivative. How to do that derivative? Remember what I did before? So two function time together, you have to derive the first one, keep the second one, and then keep the second one derivative. So it becomes, so let me use the dot on the top as a derivative. So basically, the first one, you dr dt, keep the second one doesn't change. So that's first term. Second term of this equals, this one doesn't change, cosine theta dt. Cosine theta dt, d cosine theta dt, when theta is the t function, you do d cosine theta d theta and d theta dt. Okay, so this one, we talk about it, right? Okay, now this one becomes cosine theta is minus sine theta, then d theta dt theta. So this is the first term, right, of here. The second term you can do also r sine theta, now is j, and then the second term is r sine theta dt become cosine theta d theta dt j. Got it? So in our case, it's basically r cosine theta minus r dot dr dt cosine theta minus r times sine theta. This is x direction, and what is y direction is r dot sine theta plus r theta. Let me move the theta on the top because theta is not within the cosine theta j. X component, y component of the velocity. So then the velocity amplitude equals to this p square plus this p square, and you put in. I don't want to write it anymore. Okay. Cool. Okay. So this is a velocity. right? From this based on the polar kind of characterization. So so this is when you describe the circular motion, you have to use this one. Why? So let's do a circular motion, like the orbiting case, like orbiting a planet orbiting case, or we swing a rope with a ball on at the end. We swing, we rotate. This kind of case. A car make a turn with a circular drive. So all those kind of circular case, this kind of circular case with R fixed, right? R now circular case, let's say we have perfect circular motion. So R is fixed. R is fixed, what does it really mean? Only change is theta, correct? So really means the R dt equals to 0, correct? In this case, when the radium is fixed, right? So I have a reading varies case. Say I can vary anything here, but in the example here, R is fixed reading case. What is one deduct to? So this is a special case. So this is a special case that's fixed radium circular motion. This becomes 2 watt. So R dot 0, right? So this can become minus R sine theta I. R dot 0 plus oh, sorry. Yeah, that's why I couldn't be right. So sorry, here I missed one. Here's theta. Sorry. Yeah, other cannot be right. So this is R. Let me rewrite it. So this becomes, so this one, R dot is 0. The RDT is 0 because R is fixed. So then only left is minus R theta dot sine theta I direction plus R theta dot cosine theta J direction. Remember, the velocity is along which direction? In the first case, velocity is perpendicular to the radium, correct? So really means, if you really, this is theta, where is theta? This is theta, correct? So can you understand what this really mean? This means if there's a vector as R theta dot, so that one projected to the y direction will be R theta dot cosine theta. Project to x direction will be minus, because towards that direction, opposite of x direction, minus R theta dot times sine theta, correct? So it really means the R theta is your linear speed. So this is the very important formula for the circular motion. So basically, linear speed at a fixed circular motion is radium times theta times d theta dt. D theta dt. Typically, we call d theta dt called omega, which is also omega equals to, if it's a constant motion, 2 pi divided by period, because that's d theta dt. right? If the is a constant angular motion, so d theta is 2 pi is one circle, t is a whole period. So that is 2 pi dt. So, or this is 2 pi f. F is frequency, you know, how many circle per second. So this is the whole thing coming from here. So, but this one becomes circular motion, very important relationship. Linear velocity equals to radian time angular velocity. This guy called angular velocity for here. Got it? Because we are going to deal with circular motion a lot later, good example like orbiting, like a basket spinning, water spinning in the basket. So that's why this why we need to derive here. Understand? When you go here, okay? This is where you're coming from. You write the initial position vector into you know, still projecting xy direction component, however using a polar coordinate, which is r and theta. One is angle, one is amplitude. So then r is this relationship. And then naturally, just based on the definition of velocity, which is dr dt, and using derivative basic knowledge, you quickly derive into here, right? And this is a general case. General case means r could be vary. Basically, doesn't need to do a circular motion. Could do a crazy random motion. And however, if we just consider a perfectly circular motion with radian r fixed, so the r dt doesn't change amplitude, only change theta angle. So in that case, my velocity becomes this formula, simplified from here because r dot becomes 0. This term gone. Okay, so in this case, you know, you truly understand is really from amplitude point of view, all this square plus this square equals to v. So v is this guy, right? Or you can understand the other way. So v amplitude equal to r cosine theta r square plus r theta sine theta square. So this one is this one. Okay, so v equal, so then yeah, v is radian times angular velocity. Angular velocity is dc d theta dt. Theta angle time change rate, so it's also called omega, and so that is angular velocity. So this is angular. This is velocity all clear. Okay, although dealing with special case. Now let's continue. Let's continue to let's continue. So let me rewrite here. I can continue to do A. So A dv dt. So I have to do this one one more time of derivative. So what is this? Let's do one by one. So again, this both general case, both are the time function. So we have to do, the first one is dot, second two dots, right? The first one derivative one more time, two dot. Then the second term doesn't change, right? And then plus, I will write minus first, plus this term, first term doesn't change. The second cosine theta dt equals minus sine theta d theta dt, correct? Or we can write theta dot. let me theta dot, I don't write behind the sign, I write here, correct? So this is first term here, derivative. Second term becomes minus r dot, the rest doesn't change. And then the second one, the first one doesn't change. The second one, okay, then minus one more time. This one doesn't change. This one doesn't change. Cosine theta d theta dt. D theta dt is here, so this one is square. So this is whole thing complete for the first everything under x direction. One, two, three, four, five term. Correct. Okay. Then we do the second one here. The same thing. The first one is r2 dot sine theta plus r dot cosine theta dot plus r dot theta dot cosine theta plus r theta dot dot cosine theta minus r theta dot sine theta dot square j. 1, 2, 3, 4, 5 term, correct? Okay, so this is A. This is A. Let's simplify that. I think there's something can be simplified. Let me see. Yeah, those two same. So basically become 2. Then we can cancel 1 out. Those 2 also same become 2. Cancel 1 out. Then the rest cannot do any more. Yeah, then become 4 term. Okay. Okay. Good. So now. So actually, this one, if you really want to look into, there are many interesting terms here. Once we do a simplify version, which is constant radian motion. So r equals to constant. R amplitude equal to constant. Theta change. So then r dot equals 0. Of course, r dot equals 0, right? And then we can quickly simplify that. And also we like to let's go simplify. Now A becomes 2. The first term is 0 because r dot 0. The second term is 0 because r dot is 0. The only 2 terms left. Okay. So become minus r theta dot. Remember, theta dot is omega, correct? Angular velocity. Now we change that to right angular velocity derivative sine theta minus r omega square cosine theta. This is x direction. R direction 0, 0, r time omega dot cosine theta minus r omega square sine theta j. Here is the term. Okay. So let's further simplify. Let's say we are dealing with a circular motion, which omega angular velocities change, which is angular acceleration, equals to 0. So in that case, if this one is 0, the only thing left is this one. So now A becomes minus r omega squared cosine theta I minus r omega squared sine theta j. So what's this? What's this? Well, of course, A amplitude equals square root this guy square times this guy square plus this guy square. You can very easily prove that equals to r omega square. Oh, omega square r, whatever. Okay. Got it? So which really means, which, what direction this guy is? Any idea what direction this guy is? You look at here. The direction this guy actually is for this kind of fixed motion. The velocity here is this way, right? And this is the velocity direction. The A direction actually is, this is A direction to the center of the circular motion. 所以叫向心加速度 to the center. Say that both are negative direction. If you project to the both x, y, negative x, negative y, and this is theta, so which means this is theta. So A cosine theta, sine theta. So this is exactly along the radian, opposite direction. So that the amplitude is this one, direction is the other one. Okay, so this one actually is very, very important because, can we write one more time? We know V equals r omega here. So in that case, this one become what? Correct? R squared times omega squared divided r equals r times omega squared times r. So this A equals V squared divided r equals to r omega squared. So this is central acceleration is this formula. So of course, don't forget what we simplified from here. Step here, the first simplify is r dot equals 0, dr dt equals 0, dr dt second, of course, also equal to 0. So which is simplified to to here, okay? Then we also assuming the angular velocity change rate or angular acceleration equal to 0. So that one simplified to here, which give us here. So the acceleration equal to this. So this is very important because now we will use this right away. For example, between if we Earth and we have a satellite orbiting around Earth at a height at a distance center to the center r, right? And with a constant angular velocity rotation, so we can solve this velocity distance relation right away, because we know F equals ma. So Earth's mass is m, satellite is small m, satellite movement is F equals small ma, okay, and which is now because the circular motion a equal to v squared divided by r, distance to the center of the Earth, and the linear speed on the circular motion. This is what we have from here, simple. And meanwhile, this force is gravitational force, right? Gravitational force, of course, equals mg. However, is the really because it's gravitational force 万有引力, universal gravitation according to Newton's another law, which is not F equal ma. Second law, another law, Newton another gravitational law is equals to gravitational constant, the mass of the Earth time mass of this guy satellite divided by their distance square. So that is the universal gravitation law, also applied to you and me. You and me's attraction force is also characterized by G times your mass times my mass divided by current you and me distance square. Okay. So this is a gravitational between mass of Earth and the satellite. So this one. Of course, from here you know that G equals to what? It's Gm divided R squared. So you can calculate using gravitational constant, which is physical constant available. Earth's mass and Earth's diameter. This one is 9.8 meter. You can easily get this one. Okay. So I tell you where this this guy, how to calculate this guy, but this is not what we intend. We are intended this two same, and then same this one gone. So you can derive V equals to what? V equals to Gm divided by R square root. So basically, for satellite to move around the Earth based on stable rotation, orbiting with a distance to the Earth center r, and the speed is fixed. The speed is a function of distance, but is determined by the gravitational constant time Earth. Nothing to do satellite math because it cancel out. The mass of the Earth divided by the distance square root. So we utilize what we got from circular motion, a simple, very simple circular motion. Okay, constant diameter, no angular velocity, really means theta's 2 dot equal to 0. So This is the formula. So this is a widely used formula when you do all your high school math, high school physics. Use this formula very often. We remember A equals V squared divided by R. Why? So here, it's a very general format. You more complicated here, more general, very simplified, very general case here, and even general here, and the very general here, and yeah, this So that's what I got for pretty much for today. Any question? So this is a powerful. So look like lots of math. However, if your math is good, and there's no much physics. Physics, I start from where I start. I start from just F equal ma, right? I didn't do anything. Frankly, I just use F equal ma. I use F equal ma, and what else I use? Let me review it. Oh yeah, I use F equal ma, and I just use this vector, position vector, and then rest is all math. I write down into this polar description, and then I use the what is by definition velocity is dr dt, and I start to do the derivative according to math rule or derivative definition. Then I get this. Once, of course, simplified, r dot equal to 0, dr dt equal to 0. So then from there, I do the second derivative, which is the acceleration, and then I still. So there's nothing. There's no really physics. No much physics. Physics is very simple, and the math is a little bit headache. However, once your math is solid, then rest is simple. Is that right? Okay, so I think that's it for, so once we have this formula, and then we can do all kind of interesting other math problem, circular motion math problem. For example, I already quickly gave you example how to derive the satellite speed and formula. Okay. Then we can later, next time we can do other examples like bucket spin and other things. Okay. Cool.
Yep. Thank you so much, Dr. Wang.
Yeah, I hope don't make you confused. Rather than so once you digest the math, if the math to you is no problem, dr dt, d theta dt, and those kind of derivative to you is very straightforward. Then what I derived here, you can do in just in 10 minutes. It's really quick. You can do it really quick. The only thing you have to be, you understand everything coming from F equal ma. Physics. So learning physics, two things very, very important. Okay. First, concept. Definition. Concept. Okay. You have to know what is definition. Why dr dt is velocity. Why dv dt is acceleration. Concept, understand. Math solid. You are the king. Is that good?
Sure guide to world domination. Nothing.
It's a guide to world domination, she said. If you have good math and if you understand the concepts.
Right, exactly. And so it's of course easy to say, hard to do. But I hope I give you a picture. Even though it's hard to for you at this stage, hard to digest quickly. However, I try to build you a top-down approach, I would say. I try to teach you physics different from your school. The reason is I want to make everything, eventually, once you're fully able to digest those, you are seeing, oh yeah, everything is so simple.
It's an omniscient perspective, guys.
So I hope this percept provide you something interesting angle to understand your daily. Once you really learned 1 year of physics, you are looking back saying, oh, now I understand better because I, starting from tip of the pyramid, I can go down. The only thing I need to keep in mind is concept and some math skill. Right? So that's it. It's nothing really. To be a good physicist is different skill set from being a good biologist.
What's the skill set for being a good biologist?
For being biologist, you may not need so strong so strong the math skill required or the this but you do need some memorization. You need sometimes we say biology more like a history, learning history. One of the several teachers told me biology grades correlate well with history grade. I don't know if it's true or not. I
think so block.
So seeing so many students actually biology, how good biology class grade is, just look at their history grade. If history good, biology typically is good. However, history good, physics may not. So it's different.
I mean, bio starts hitting you with like the hard math later on. It's like when you thought you know everything, and now people ask you about Gibbs free energy, and you're like, oh, wow, math. And like also titrations, oh my god.
But free energy, of course, it's also physics concept, and but used more often in chemistry actually, right? So biology basically borrowed that concept from chemistry, I would say, or physics.
Yeah, bio has like simpler math applications. We're mostly doing like harder algebra. We never really go to calculus.
Right. You don't need it. If you are dealing with biology using calculus, that's probably you are building some of the molecular structure, basic design of biological molecule. That's only at that stage you may need. So, but that's when you're building a biological molecular structure, that's basically is physics. I wouldn't even call it as biology anymore. You know what I mean?
Yes.
I'm a little bit biased sometimes, but that's okay.
Yes. It's all physics in the end, just to be sure, unless it's math.
Okay, cool. So that's for today. And again, any question, just I expect some, of course, I am, it's sad to say someone, like Nick is not coming anymore. And I think Paul, I told Paul probably he shouldn't join anymore because it's really hard for him to follow because he couldn't understand the trick. So basically, why is this projection are cosine theta? This kind of thing, he has difficulty in quickly grasp this concept. Then that's why I said, okay, Paul, it's probably time to note. You don't need to do sitting in this class. You can watch my recording is fine, but I don't think it's wise for you to stay here. Why not spend that time on your learning more trigonometry or math or something else? So that's more fundamental thing, because it's really hard to understand. Understand if you are able to follow with me through without much big problem. So you are pretty solid on your understanding on derivative and trigonometry and all those as foundation, right? So if you don't have that foundation, it's really hard to follow. And but I wouldn't say if you cannot follow 180%, you should drop out of this class. But if you only can understand 5%, you should, right? But if you are able to handle half of them, saying, oh, I roughly get your idea, I may need to go back to check on certain concrete things, that is fine. You can watch the recording again and then try to derive some formula yourself until you, aha, now I understand. So that shouldn't be too hard, right? Okay. But again, welcome anytime. Talk to me, and I can explain it one more time, or I'll answer other questions. I will be able to have opportunity to address. But otherwise, I will see you later. Okay.
Thank you so much.
Yeah, I hope I can move quickly over. The reason I move very quickly through is because I do hope I can teach something else. Not just this, right? Unfortunately, those are something we cannot easily, work around it before we can do something more interesting stuff. That's sad. But I hope this helped for you. And but I do believe you can digest the most part of this class when you go back to school and look at what you learn related to those one. You will have much better, clear picture. That is not for you easily to grasp it from your school knowledge. That's what I believe. I might be wrong, but that's what I believe. Yeah. Okay, cool. Okay, bye bye.
Thank you so
Thank you,
much.
Dr.
Bye bye.
Bye bye.
Bye.
Yeah.
Thank you.